Okay, so we've been talking about this idea called oxidation number. And depending on the oxidation state a given element, atom, ion is in, it will behave very differently. So actually, our demonstration specialist, Philip, posted this on his Facebook today, and it seemed apropos. This is vanadium. So this is a metal, and what's written on each of the vials is the oxidation state it's in. So vanadium in a +2 oxidation state has this purple color, and +3 it's more of a like kind of aquamarine. +4 it's blue. +5 it's yellow. Just kind of a take-home point is the oxidation state of something will affect its properties. In this case, we can see it through color, but it also affects things in terms of like what it can do in our body. Like iron 2+ is good at helping transport oxygen around, but iron 3+ not so much. Iron solid is structurally secure. Iron 2+ is rust. So depending on the oxidation state, you get a lot of different effects in materials. And this is the last slide we did. We were talking about the concept of spontaneity and work. And the idea behind spontaneity is, will it happen? And with the dam, we said, it will happen. The water will flow over. It'll go from a higher basin to a lower basin. So this process can do work. Anything that's spontaneous theoretically can be harnessed to do some sort of extra process. So like in this case, the water goes over a turbine, it spins the turbine is then used to generate electricity, yada, yada, yada. Whenever you have the reverse of a spontaneous process, that's non-spontaneous. You have to put work in, energy in order to get it done. So in the case of the dam, we would need to scoop up water and then walk it back up to the top and dump it, or we could get a pump to do it too. Regardless, it requires energy, it requires effort, it requires work to get it done. Okay. And so we finished with this clicker question, which was, which of them can do work at room temperature? The answer was B. B is our combustion reaction. It's our hydrogen exploding, and it's what propels rockets into space. A is what's called electrolysis of water. It's splitting water into hydrogen and oxygen. If this could spontaneously occur, then space travel actually might be a little bit more easy, because then you could just have water and you can have it spontaneously giving off oxygen that you need to breathe. But it's not spontaneous until you get above like 1300 degrees Celsius. So not that feasible for creating oxygen to breathe. Okay, so now we're going to talk about, just from an energy standpoint, what is it that makes something spontaneous? And it turns out that what makes something spontaneous is the ability to form a more stable, lower energy product. An analogy that we used earlier in the semester that I really like is, what is more stable? A kindergarten classroom during a low energy time, like nap time, or a kindergarten classroom after the teacher, for some reason, gave all the children Red Bulls? I'm not sure that that's legal, but which one's going to be more stable? The low energy, the chill time. Chemicals are the same way. The more relaxed they are, the more stable they are. And it turns out that's what drives reactions. So if we were to consider energy, if we have our reactants higher in energy and our products lower in energy, that's what creates a favorable reaction. And so we're going to, in the context of electrochemistry, how we can get electrons to move from one thing to another. But the idea is, if something can go from a higher energy state to a lower energy state, that's favorable. But energy can't be created nor destroyed. We can't just, say, okay, it was here, it's down here, end of story. So what happens to that energy? Well, it could be transferred into a number of different ways. It could be turned into like heat, for example, or it could be used as electricity to light up a light bulb. So we call this energy actually free energy because it has to go somewhere. And it got this name because this energy is theoretically free to do work. It can be done to accomplish something that we want to get done. So in the case of a battery, for example, the energy that's released from going from a higher energy state to a lower energy state can be used to power our laptop. It's free to do that, where this kind of naming convention came from. And that's what we're going to be focusing on today, is how some materials can be paired to create current. So this energy that's given off can be then done, can be utilized, harnessed to do things, make things happen. So work is just basically, for our purposes, the ability to make stuff happen. And it turns out there's a lot, many, I mean, this dictates all of the reactions that occur in the universe. So a good example of that, a biological example, is ATP, or adenosine triphosphate, is a high energy molecule. It has these really high energy bonds that when they dissociate and it's transferred, like you get the reaction to occur, energy is given off. And so that energy can be used to do things that aren't necessarily energetically favorable. It can lend its energy to help our body do things. And a good example of that is making proteins. It takes energy to put together all these different monomers to make a giant protein. But enter an ATP, it will react and it will lend its energy out to facilitate this process. So the context that we're going to be looking at is voltage. We're going to be looking at batteries today. And the key idea here is voltage is basically a measurement of the willingness of a redox reaction to occur. So it's the ability for electrons to be transferred. And the greater the voltage is, the more work can be done. And we might be used to this from using batteries. If you have a small task that you need to get done, you can use like a AA or a AAA, a 1.5 volt battery, and that can probably facilitate a process like operating a remote. If you have something more intense, like operating a cellular phone or a laptop, you need more voltage. So we use 3.4 volt batteries to do that. If you want to operate a car, you need even more voltage, etc. So enter this idea of electric potential difference, voltage. It is the ability to do electrochemical work, to make electronic things happen. Okay? And what we're going to see today is that there's some chemicals that really like to be reduced. They really want to gain electrons. There's some, however, that really want to be oxidized. They want to get rid of their electrons. If we compare together something that wants to get rid of electrons with something that wants to gain electrons, then we get a very favorable reaction. And if we happen to pair those with a wire between them, then we get current and electricity. So these things down here, we have a whole slew of different types of batteries. These take advantage of this whole idea of free energy in the context of. So what we're going to do is first look at this little diagram here. This is what's called a NiCad battery. NiCad batteries were some of the first really prevalent commercial batteries. They used nickel and cadmium, which is how they got their name. So the way that these batteries work is that we have here these are higher in energy. These ones down here, these products, are lower in energy. And so naturally, if you pair together solid cadmium with nickel 2+, the cadmium will spontaneously get rid of its electrons and give it to the nickel. And if you pair them through a wire, then you end up getting current. So the energy difference between these two, again, can be used to do work, make things happen. And these are what's used in what's called a NiCad battery. And those are like the classic type of, they're not used as prevalently today. I mean, they're still used to some extent. but these are like the original copper tops and whatnot. Are there any questions about this kind of concept? We have higher energy materials, they form lower energy materials. What happens to the energy? It's given off. And that's what facilitates powering our electronics. Are there any questions about that? Alrighty. So now let's talk about a way that we can see through numbers if something is favorable or not. So we have a whole slew of reactions here. And what we're going to do is we're going to stick basically a price tag onto these reactions. We're going to see if each one is favorable or not. And then we're going to see what that means in the context of a voltaic cell / battery. So using this convention up here, that is E with a degree sign and then red. The red means reduction. The E means voltage. And the idea is the more positive the value, the more favorable it is. The standard sign is just used, so this, this degree sign up here is just used. Voltage changes at every given temperature. We'll talk about what that standard sign means actually on the next slide. But it just means at 25 degrees Celsius, which is kind of a chilly room temperature. But anyway. Okay, so if we look at fluorine, what do we know about fluorine in terms of, does fluorine tend to attract electrons toward it in our experience throughout the semester? Is fluorine an electron hog, or does fluorine usually push its electrons away? Thoughts? The chat box. Excellent. It attracts electrons. Fluorine's an electron hog. It loves to bring electrons in. So if we look at this reduction potential, it's positive 2.87 volts. So what that means is the reduction of fluorine gaining 2 electrons. So what we're doing here is we're reducing ends up being a very, very, very favorable reaction. So say, that's pretty favorable. How about gold? So gold, we haven't talked that much about gold. Gold is represented by AU, but it turns out it has a reduction potential of 1.69 volts. Positive voltage means favorable, so that's pretty favorable too. Now, this one that's offset in red, Na plus plus an electron yields Na solid. Let's see what that voltage is. Negative 2.71 volts. So what this means is if sodium is in its +1 oxidation state, it does not want to gain an electron. Once it's at that +1, stable, it's content, happy as is. So as a result, it's not going to readily accept an electron. Okay? And if we look at sodium and our experience with sodium, whenever we use sodium, it's usually in the form of a salt. It's like NaCl, for example, where it is in that +1 oxidation state. Okay. All right, so what happens if we flip around a reaction? The reverse of a reduction is an oxidation reaction. If we flip around a reaction, we're doing the opposite process. So any thought as to what will happen to the voltage if we reverse a reaction and we're doing the opposite process? Any thoughts as to what will happen to the sign? So let's say, for example, we took solid gold and we wanted to pull an electron away from it. So in this particular case, what we're doing is oxidizing gold. Then what's going to happen is we're going to take our potential and we're going to flip the sign. So instead of being positive 1.69 volts, it's going to be negative 1.69 volts. So whenever you oxidize a metal that's solid, you corrode it. Like iron, when it oxidizes, becomes rust. So negative 1.69 volts means you have to put in a lot of energy to pull an electron away from gold, which probably matches our experience with gold. Have you ever seen a friend who's really upset? You say, friend, why the long face? And they say, well, my gold rusted. Probably not. Gold doesn't tend to do that. And that's one of the reasons why it's such a precious earth metal, is because it's really adverse to getting oxidized, to losing electrons. So this is unfavorable. This E standard oxidation means the standard potential of a given oxidation reaction. It tells us how favorable it is to pull an electron away from something. And just like with reduction potential, more positive voltage means more favorable. So if we flip around the sodium reaction, we get sodium solid turns into Na plus and E minus, and that has a positive 2.71 volts, which is very, very favorable. Which gives us actually a good opportunity to play a short clip that we did. We played this early in the semester, but I think it's pretty interesting. It kind of showcases this whole idea. Let me pull this up. For it, here we go. Okay. So let's see what happens if we put solid sodium in water.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
So that is what happens with sodium when it meets water. The sodium gets oxidized, the water gets reduced, and you could theoretically pair this sort of reaction through a wire, but if you don't have a good way of harnessing it, you get that sort of effect. So it's very, very, very favorable.
This is a solid chunk of sodium metal. This is number 11 on the periodic table of elements, and it is is extremely reactive if it comes in contact with water. So a few months ago, one of you left a comment asking me to flush a piece of sodium down a toilet, which seems like a ridiculous request, but I have got code.
I'm curious where that's going, but forgot to stop the video. Okay, so behold, a list of reduction potentials. So this whole thing tells us how favorable it is for something to gain electrons. And what this basically shows us is the higher up we go, well, first let's define what it means to say standard conditions. Standard conditions assumes that everything is 1 molar. These values change based off of the relative concentrations and off of the temperature. But we're just going to be looking at 25 degrees Celsius and 1 molar. These are all relative to each other. A redox reaction can never take place in a void. Something has to gain electrons for something else to lose electrons. So actually all these numbers are relative to each other. They're actually made up with respect to a standard. The standard that was used is H plus gaining electrons to become hydrogen gas. So all of these other numbers are based off of that. And potential is a way of measuring the favorability of a redox reaction. More positive means more favorable. So the higher up we go, the higher up this gets, the more favorable, which means fluorine here is the element or is the molecule that most wants to gain electrons. If we look on the bottom shows us what doesn't want to gain electrons. Lithium kind of takes the cake there. Very, very unfavorable. Okay. So now let's combine 2 different half reactions and get an overall potential for it. And we're going to look specifically at the reaction for iron rusting. So whenever we want to find the oxidation potential of something, if we know the reduction potentials, and if you flip the reaction, if you go from reduction to oxidation, what you end up getting is the oxidation and you flip the sign. So we can find the overall voltage of something by taking the reduction potential of what's being reduced, i.e. E degree sign red, and add to it the oxidation potential of what's being oxidized. So when you have these 2 processes coupled, when you add together the 2 voltages, you end up getting the overall voltage for a reaction. So specifically, we're going to look at iron rusting. Iron rusting takes place in the presence of oxygen. And this is the reaction that generally speaking occurs. We have O2 gas. It's even more favorable in acid. Remember, acid has a lot of H plus. And oxygen loves accepting electrons. Oxygen's up there. And so this whole reaction here ends up having a very favorable positive 1.23 volts. The oxidation of iron, on the other hand, so iron going from a solid to iron 2 plus, iron corroding, well, it turns out that's also favorable. It has a standard oxidation potential of 0.440 volts. So if we combine these 2 reactions together, when we combine them together, the number of electrons checks out. So the number of electrons cancels out if we were to combine these together. And we end up getting this overall reaction, which is oxygen plus iron, especially in the presence of H plus, yields water. And we can see here that our iron has gone from solid to aqueous. So this actually dissolves, it literally dissolves our iron. And in order to get the overall voltage from this, we take the two potentials, we take the oxidation potential of what was oxidized, we take the reduction potential of what was reduced, and we just add them up. And when we do, we end up getting positive 1.69, or we end up getting positive 1.67 volts. Are there any questions about that? Okay, so since there were some questions on oxidation number, I want to take some time to do some practice with oxidation numbers. So that's precisely what we're going to do now. Okay. So we went through the different rules of assigning oxidation numbers. And something that I should have emphasized, I was not clear enough about it, is that if you have a neutral molecule, if you just have a neutral element, and it could be a solid, it could be a liquid, it could be a gas, but if you just have a single element and it's neutral, then its oxidation state is just going to be 0. If you have an ion, then its oxidation state is going to be equal to whatever the charge on that ion is. So let's just go through and look at each of these. Up first, we have oxygen here. Here we have just the element oxygen. It has a neutral charge overall. So that means its oxidation number is just going to be 0. Now, up next, we have H2O. If we have different elements combined, then we need to start using those rules that we had from Wednesday. And whenever you have a group 1 element in a molecule, it's going to be +1, but there's 2 of them, which means that total hydrogen is contributing this oxidation state of +2. And then remember, all the oxidation numbers need to add up to the overall charge on the molecule. So since this is neutral, that means the oxygen needs to be -2 here. So we have the 2 positive ones and the -2, and they cancel out. Then we have fluorine, F2. Well, neutral fluorine, again, is just going to be 0. And then finally, we have iron 2+. Whenever you have an ion, its oxidation state is just going to be equal to the charge on that ion. So this is just going to be +2. So now let's do a more interactive version of this. So we're going to look at some more complex molecules here. And I want us to do this in a poll style. So up first, we have this H2SO3. And the question is, what is the oxidation number on this sulfur? So we'll go to the polls and take a moment, use the rules from Wednesday. And let's see what we end up getting. And feel free to ask questions, or either in the chat or through microphone. All right, we'll give this another 5 seconds or so. So 5, 4, 3, 2, 1, and 0. And the answer is dun, 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 D. Nice work. So the way we would do that is each hydrogen is +1, but there's 2 of them. So hydrogen is contributing, we can think of it as a charge, an overall charge of +2. Oxygen, on the other hand, is typically -2 for a total of -6. So that means that we have the sulfur here, it must be +4 because everything has to add up to 0 when it's all said and done. All right, well done. So up next, we have this calcium carbonate. And we're looking at the carbon. And go. And we'll give this one 45 seconds as well. If you do have any questions, please let me know. All right. So let's please get our answer in 3, 2, 1, and 0. Excellent. Once again, it's actually +4. So calcium is in group 2, which means calcium is +2. Oxygen is -2, but there's 3 of them for a total of -6, which means calcium, just like sulfur in the previous example, is +4. But wait, there's more. Here we have iron oxide. And we're looking at the iron here. So I want to know, what is the charge on each iron? And away we go. So what is the charge on each iron here? And we'll give this one up to the 35-second mark. But so far, so good. Okay, please get your answer in 3, 2, 1, and 0. Nice job. The answer is C, +3. Excellent. So each oxygen is -2 for a total of -6, which means that each iron must be +3 because the iron total has to be +6. We have a question. We're just looking at the individual atoms. So whenever you're asked about what the oxidation number on something is, we're looking at the individual atoms here. Good question, very good question. All right, we've got one more. ClO4-, and I want to know what is the oxidation state on the chlorine there. So take a moment. Good, this is looking very good. All right, please get your answer in 5, 4, 3, 2, 1, and 0. And our answer is E. So each oxygen is -2 for a total of -8. But the whole thing has to add up. So the whole molecule has a -1 charge. So when we add these all together, they have to equal -1, which means that the chlorine must be +7. Very good. Any questions about these? Okay, so then let's look at a few reactions and say if something's being reduced, oxidized, if it's the oxidizing agent or reducing agent. So up first, we have this reaction. Aluminum oxidizes really easily. If you look at aluminum cans, they actually have aluminum on the inside of them, but they're surrounded by this coat of aluminum oxide because aluminum basically, if it touches oxygen, will instantly oxidize. So my question is, in this reaction, is aluminum oxidized or reduced? So for these first two, we'll take about 30 seconds, and then we'll do a speed gauntlet of these. So what's happening to our aluminum in this reaction? Okay, please get your answer in 3, 2, 1, and 0. For some reason, 5 people picked C and D. Those weren't answers. Um, the answer is indeed A. Good, it's being oxidized. So it's going from 0, because it's a neutral metal here, up to +3. So if its charge goes up, that's oxidation. Okay, next question. What about the iron 2+? What's happening to it? And go. Once again, I'm getting trolled with C and D answers. Please get your answer in 3, 2, 1, and 0. And the answer is indeed B. So it's going from 2+ to 0. So it's starting at 2+, it's going down to 0. It's quite literally reduced. So this one's oxidized, this one's reduced. How about this reaction here? What's happening to chlorine? Is it getting oxidized or reduced? Please get your answer in 3, 2, 1, and 0. Very, very good. Excellent. The answer is B. So it's going from 0 to -1, which means it is being reduced. How about iodine? We'll give this one 15 seconds. So is iodine being oxidized or reduced here? And please get your answers in 5, 4, 3, 2, 1, and 0. Excellent. The answer is A. It's being oxidized. It's going from -1 to 0. So this is oxidized, this is reduced. So up next, just by the naming convention, will we call aluminum the oxidizing agent or the reducing agent here? Okay, this is looking good. Please get your answer in 3, 2, 1, and 0. So remember, whatever gets oxidized is the reducing agent, so choice B. Very good. And then how about the iron 2+? Is it an oxidizing agent or a reducing agent? Please get your answer in 3, 2, 1, 0. Very good. It is an oxidizing agent. So whatever is oxidized is the reducing agent, whatever is oxidized is the reducing agent, whatever is reduced is the oxidizing agent. And the same thing holds for this and all redox reactions. Are there any questions about that? Anybody? Okay, so now what we're going to do is we're going to pair this all together and we're going to build ourselves a battery. So the way that batteries work is we pair together something that really wants to be reduced with something that really wants to be oxidized. The thing that wants to be oxidized loses its electrons. And so down here, we kind of have a diagram of electron flow. The electrons start here and they journey around. And eventually they get to something that they can do work on. In this case, a light bulb. So the movement of electrons allows this light bulb to shine. So some naming conventions. These are known as Voltaic cells. Voltaic cells are these collections of materials where you pair something that's getting oxidized and something that's getting reduced. And one of the most widely known forms of these, more commonplace name, is a battery. So voltaic cells, batteries are a type of voltaic cell. Another convention is whatever's getting oxidized, we call that the anode. Whatever's getting reduced is called the cathode. And so the way that I like to think about it is that electrons travel in alphabetical order. So they travel from the anode and they end up at the cathode. So whatever's oxidized is the anode, whatever's reduced is the cathode. So here is a table that we'll be coming back to for the remaining 5 minutes of class today. And what it does is it gives us a whole plethora. There's an information overload here, but it tells us the reduction potential for any of these materials. And there's a non-trivial amount. So for example, if you want to know the voltage of reducing silver, which is Ag+, we would look until we see silver, and then we would look at the value that goes with it. Okay, so we're going to come back to this in just a moment. And we're going to build ourselves a battery. First, before we can build that battery, we want to pair together two materials that are going to give us a lot of voltage. So here I've got three different candidates. We've got aluminum 3+, iron 2+, F-, and Au+. Actually, I want to change the F- to Cl-, just for the sake of. So we're going to change this. It actually won't make a difference, but I'm going to do Cl- instead. Okay? So my question for you is, which of these is going to give us the highest voltage, the greatest reduction potential? So we have our answer choices up here in the top right corner. So take a moment and look, see if you can find these different materials and see if you can predict which one is most easily reduced. It would help if I could click competently here. Right, so I'm going to open up a poll. And it takes a decent amount of time because there is a lot of information on here. So see if you can be, it's basically like a scavenger hunt, only less fun. See if you can find these. And once you have, please tell me which one is the most favorable. Nice job, y'all. This is looking good. I'll give us another 20 seconds or so. please get your answer in. In 3, 2, 1, and 0. And very good. It is gold. So, aluminum 3 plus, the reduction potential of that is negative 1.66 volts. Ah, that's not favorable at all. Iron 2 plus is negative, actually, no, sorry, iron 2 plus is negative 0.440 volts. That's the wrong value, but still not favorable. Chlorine, well, chloride. Turns out that Cl minus doesn't have a value on there. It's nowhere to be found. So it's non-applicable. And then finally, Au plus, going to solid gold, is positive 1.69 volts. So the most favorable one is gold. So gold is going to be in our battery. It's going to be a baller battery, but we need to pair it with something that wants to be oxidized. So the follow-up question for you is, which of these 4 things are we going to pair it with? One moment. Let's bring up the table again. So we looked at what wants to be reduced. Now our goal is to figure out which one is easiest to oxidize. So let's get that poll a-rolling. We have our answers in the top right-hand corner. And think about the relationship between reduction and oxidation. Oops, here are the letters. Good, good. This is looking good. So we'll give this another 15 seconds or so. Okay, if you haven't gotten an answer in yet, please get your response into this poll. In 3, 2, 1, and 0. And our answer is indeed A, lithium. So if we look at lithium, lithium is down here in this corner. And reducing lithium carries a price tag of negative 3.05 volts. Not very favorable. However, oxidizing lithium means we would take the opposite sign. So lithium would be positive 3.05 volts. Manganese would be positive 1.18 volts. Sodium would be positive 2.71 volts. And iron would be positive 0.440 volts. So all of them are favorable, but lithium is the most favorable. So this is actually why lithium is used in our cell phones, in our laptops, etc. It contributes a lot of potential when it's oxidized. Lithium loves to give up its electrons. It's a really, really, really good anode. So lithium is element number 3. Can anybody think of another reason why lithium might be good for portable electronics? It's really easy to oxidize, so it's very favorable. It's great in redox reactions. But from a practical standpoint, why would element number 3 be useful in a portable electronic? If we have a portable electronic, what sort of characteristics do you look for in something that you're going to be carrying around with you all over the place? Any thoughts? So it turns out that another advantage of this is the fact that it's really, really, really lightweight. Yep, and so that's why we use it in our cell phones, because lead, on the other hand, really heavy, would weigh us down. We don't want to carry around a lead battery with us. Cars can do it, that's fine. It's also really toxic. Lithium, on the other hand, lightweight, really easy to oxidize, contributes a lot of voltage, and so it's kind of like a perfect 1-2 punch to make for portable batteries. So on that note, we will finish up. We'll talk a little bit more about this on Wednesday. We'll review on Monday. We'll also talk about a little bit about neurons and how electric signals can be transferred throughout the body, which I'm excited for as a biologist myself. And thank you all for your time. I hope everybody has a spectacular weekend. And I'll see you either at the review on Monday or in class then on Wednesday. So thank you all for your time. Have a great day.